Welcome, automotive efficiency experts, to a fascinating dive into our machine learning course. I'm thrilled to guide you through this episode, where we'll explore a regression task using a classic dataset and a powerful explainability tool. I'm working in Google Colab, walking you through each step with precision so you can follow along as we predict fuel efficiency for cars. Let's get started by setting up our environment and gathering our tools for this fuel economy journey. I begin by installing the interpret library in Colab with the command pip3 install interpret. This library will enable us to use ShapTree for explainable AI, helping us understand our model's predictions. Next, I import the essential tools: NumPy for numerical operations, Pandas for data manipulation, and Sklearn's train test split to split our data, decision tree regressor for our model, and our square score and mean squared error to evaluate performance. From interpret, I import ShapTree from the graybox module, our tool for local explanations, along with the show function to display results. I also import Matplotlib's pyplot for potential visualizations, though we'll focus on interpret's built-in plots. I set a random seed to 42 using NumPy's random seed for reproducibility. With our tools in place, let's load the data. I load the auto MPG dataset from the UCI repository using Pandas read CSV function, fetching it directly from the provided URL. I define the column names to match the dataset structure: MPG, cylinders, displacement, horsepower, weight, acceleration, model year, origin, and car name. The dataset uses? For missing values, which I handle with the NaValues parameter, and I separate columns with whitespace using SEP. I drop the car name column since it's not needed for prediction, drop rows with missing values, mostly in horsepower, and rename MPG to target for consistency. I print the first few rows to examine the data. The first row shows target 18.0 to 18 miles per gallon, cylinders 8, displacement 307.0, horsepower 130.0, weight 3,504.0, acceleration 12.0, model year 70, and origin 1. The next row has target 15.0 to 15 miles per gallon, cylinders 8, displacement 350.0, horsepower 165.0, weight 3,693.0, acceleration 11.5, model year 70, and origin 1. This dataset includes 392 samples, after dropping missing values, of cars from the 1970s and 1980s, with 7 features and a target, MPG, ranging from 9 to 46.6, making it a great dataset for predicting fuel efficiency. Let's prepare the data for modeling. I split the dataset into features, and target X includes all columns except the target, the 7 features, and Y is the target, miles per gallon. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 313 training samples and 79 test samples. The features are all numeric, representing car characteristics, and after dropping missing values, we're ready to train our model. I initialize a decision tree regressor from Sklearn with random state 42. Decision tree regression is a tree-based method that recursively splits the feature space into regions based on feature values, making decisions at each node to minimize the variance in the target within each region. It then predicts the average target value for the region a sample falls into, making it interpretable but prone to overfitting if not tuned. I call fit on X-train and Y-train to train the model, allowing it to learn how features like weight and horsepower influence fuel efficiency. Once trained, I make predictions on X-test with predict, storing them in Y-pred, and evaluate with our square score and mean squared error. The results are printed. Our square score is 0.7761 to 77.61% of the variance explained in the test set, a solid performance. Mean squared error 11.4285. Take the square root, about 3.38 miles per gallon, which is reasonable for MPG values ranging from 9 to 46.6, though it suggests some error on extreme values. I use ShapTree from Interpret's graybox module to explain our model's predictions locally. ShapTree is an explainability tool optimized for tree-based models like decision trees, providing exact SHAP, Shapley additive explanations, values. SHAP values assign each feature a contribution to the prediction, based on game theory, by calculating the average marginal contribution of a feature across all possible feature combinations, ensuring fair attribution. I initialize ShapTree with our decision tree model, XTrain as the background data, and the feature names from XColumns. I generate a local explanation for the first test sample with explain local on XTest's first row and YTest's first value. Name SHAP local explanation. I extract the explanation data and print the results. Predicted 23.0, true value 26.0, a difference of 3 miles per gallon, which is close but indicates room for improvement. Feature contributions show displacement 2.9232, the largest positive contribution, pushing the prediction up significantly, likely due to a larger engine displacement, increasing fuel consumption. Weight 0.8626 and horsepower 0.6645 also push the prediction up, reflecting heavier cars and more powerful engines, reducing MPG. Model year minus 3.5045 is the largest negative contribution, pulling the prediction down, indicating older models, like model year 70, are less efficient. Acceleration minus 0.3663 and origin minus 0.0776 also reduce the prediction, while cylinders minus 0.0020 has a negligible impact. The visualization likely shows a bar chart with displacements bar at 2.9232 in orange, pushing right, and model years bar at minus 3.5045 in blue, pulling left, providing a clear breakdown of how features shape this prediction. Let's dive deeper into these outputs. They're a roadmap for fuel efficiency insights. The first row showed a car with target 18.0 to 18 miles per gallon, cylinders 8, displacement 307.0, horsepower 130.0, weight 3,504.0, model year 70, and origin 1, while the next had target 15.0 to 15 miles per gallon, cylinders 8, displacement 350.0, horsepower 165.0, weight 3,693.0, and origin 1, suggesting high displacement, horsepower, and weight reduce efficiency. The local explanation predicted 23.0, true value 26.0, a 3 miles per gallon underprediction. Displacement's contribution of 2.9232 aligns with the head's high values, 307.0, 350.0, indicating larger engines lower MPG. Weights 0.8626 reflects the heavy weights, 3,504.0, 3,693.0, reducing efficiency, and horsepower 0.6645 matches the high values, 130.0, 165.0, further lowering MPG. Model years minus 3.5045 is significant, as model year 70 indicates older, less efficient cars. Acceleration minus 0.3663 suggests slower acceleration. 12.0, 11.5 slightly lowers the prediction, while origin minus 0.0776 with origin 1, USA, has a minor negative effect. Cylinders minus 0.002 being near zero is interesting, possibly due to all cars in the head having 8 cylinders, reducing its variability. ShapTree's local explanation provides a clear view into how each feature drives this car's fuel efficiency prediction. To wrap up this fuel efficiency analysis, we've explored the Auto MPG dataset, a 392 sample study of 1970s and 1980s cars, and trained a decision tree regressor, achieving an R-square score of 0.7761 and mean squared error of 11.4285. The local explanation via ShapTree revealed displacement and model year as key drivers for a prediction, offering a transparent view into our model's reasoning. Decision tree regression's splitting approach captured car efficiency patterns, and ShapTree's exact SHAP values provided precise feature contributions. Grab this code, experiment with tree depth, and dive deeper into automotive efficiency. I'm energized by this efficiency insight. Hope it's fueled your curiosity about data-driven automotive analysis. See you next time for our final course episode.